Hello, my name is Mark, and in this video I want to present yet another hot plate device. I need to be able to solder BGA and QFN packages in some reliable way. But at the same time I don't want to have some semi-professional reflow station. I simply don't have space for that. There is few other DIY projects for similar devices, but they don't satisfy my requirements by 100%. So that's why I decided to develop my own variation of such hot plate device. As usual, at the start of the project I prefer to draw some high-level diagram. Hot plate is pretty simple device. Power from Type-C connector is forwarded to metal ceramic element and is controlled by pulse width modulated signal from microcontroller. Microcontroller decides duty cycle for that signal based on thermosensor and selected program. We don't need to have high accuracy for thermosensor, so we can pick a regular NTC thermistor instead of platinum-based PT100 or PT1000. Here is footage of assembly for the first PCB prototype. And of course it had some issues and non-optimal blocks, but it worked. You can see the difference between two revisions. Originally the board contained the Wheatstone bridge, used to measure a resistance from the thermosensor in a more accurate way, and circuit for single action reboot to bootloader mode for easier firmware updates. But then I thought that debug headers would be enough. Let's talk about jobs that should be done by our device. Reflow is a multi-stage process and usually is done in non-linear way. Of course, you can perform reflow by using your heat gun, but for best and stable results it's recommended to use reflow profile. First stage is preheating zone, to increase temperature of the board and components to the point when solvents and flux from solder are starting to work. Then soaking zone used to equal temperature of different parts of the board. We are using much slower temperature increase rate to cope with thermal inertia. Real work starts from temperature of solder melting point. And to achieve good results we need to reach at least 25 degrees more than melting temperature. Overall, a reflow period should take a minute or two. At the last we just cooling PCB down, but we need to care that we don't do it too fast, no more than 3 or 4 degrees per second, or we would introduce thermal stress to the soldering joints. The software part to implement such flow is not that complex. We just follow that profile. And our reflow program describes few stages, with the target temperature and ranges of acceptable heating or cooling rates. Worth to mention that we don't need to measure temperature too frequently for a few reasons. Main reason is that this system is very inertious, and reaction to our action would be slow. So we can have 5 seconds between checkpoints in which we are deciding if we need more or less heat. There are two kinds of stages, to keep desired temperature or to keep desired temperature change rate. For sustaining stages, we just try to keep the real temperature close to the target for the specific period of time. For the second kind of stages, we just check difference between temperature value now and 5 seconds ago, and making sure that it fits into the specified interval. Software and board are done, and now we just need the chassis to hold all pieces together. I was worried a bit that heat from heating element can damage case, PCB or display, so I did thermal simulation. I have designed assembly in SolidWorks with all components of the system, then declared materials for them, set initial temperature as 20 degrees of Celsius and 240 degrees for the heater, and run simulation for 200 seconds. From overall view, we can see that case is not affected much by the heat, but it's hard to see what is going on with PCB. Here is detailed view for the board, and you can see that we have just local high temperature points on connection between PCB and standoffs. That's why I used additional washers made from ceramic fiber paper for better thermal insulation. And for safety, I have chosen PA12 nylon material for the case, because it has higher operation temperature than regular plastics. The device assembly was more or less straightforward, so let's test it. Unfortunately, I wasn't able to achieve high temperature because of limitation of my power supply. MCH element is designed for 150 watts, and I fed at most 100. But in microscope I saw that lead-free solder melts and then forms good solder joints, which I have tested with dental pick later. I had no solder paste nearby for better visual effects, but looks like my device is working. To be honest, I have mixed emotions. I am a bit disappointed with the peak temperature after the real test. Even with my current power feed, the heater element itself was able to achieve 230 degrees. But with the plate on the top, it was just about 205. From the other side, it's working. And I guess if I would not be satisfied with soldering quality in the future, I always can use power supply which supports Power Delivery Protocol 3.1, and it would allow me to use 240 watts of power. It definitely would be enough power to reflow components even by using lead-free solder, which is great. Thank you for watching, and the link to repository with all necessary stuff you can find in the description. Bye.